What is up, most distinguished patrons of this channel? So for today, I have a treat for you, and it's a long time coming, and that is we're going to experiment with silicon bronze and aluminum bronze. And we're going to bend test this stuff and see how strong it really is. And I'll be honest, the results might actually shock you. So anyways, let me get this table cleaned up and let's get to work. So a lot of you guys out there have asked me to do bend tests on brazing, and that's kind of what we're going to be tackling today. Now, we're going to be doing it with the TIG process and not oxy-fuel. I know a lot of you guys have been wanting to see oxy-fuel videos, and I will get around to it. I've just been so busy, I haven't had time, unfortunately. However, we will be focusing on TIG brazing today. One of the things you guys got to understand is with TIG brazing, just like with MIG brazing, which yes, you can braze with the MIG process. I'll have a video out on that at some point in the near future. But you're not using what's called capillary action with this. You are more or less melting it and adhering it to the base metal, but you're not using flux and you're not heating something to allow it to flow into something. Like you're not clamping this plate down and heating it and allowing the braze to join underneath this plate. We're merely using it kind of like a weld that doesn't penetrate at all. The goal with this is to have zero penetration, and to demonstrate that, I'm going to do a couple test plates and we'll cut and etch them, and we'll look at that to get a better idea later in this video. So anyways, the two main types of wire we are going to be focusing on using today are what's known as silicon bronze and aluminum bronze, both of which are bare wires and both of which are designed to be used with TIG. Do not use bronze rods that are bare that are meant for oxy-fuel and attempt to TIG weld with them because, well, for one, you're going to zinc fume fever yourself and you're just going to contaminate your tungsten. That's particular rod sold at like Tractor Supply and all that for torch brazing is incompatible with TIG. You have to get TIG compatible fillers. Now, with that said, I do have a video out dealing with bronze brazing with TIG, so I'm not going to be covering a lot in this video on how to use this stuff. Please, the link is in the description. Please watch that video if you want to learn how to use that product, but we're going to just kind of make test welds more or less today. Now, there is a strength difference between the two of them. Aluminum bronze tends to be stronger than silicon bronze, and I think the test results today will conclusively prove that. I'm not positive, but I believe it will. So that's something to be aware of. Another thing to be aware of is I find that aluminum bronze wire with TIG tends to run better on AC than DC. It produces a cleaner puddle and it might help with adherence to the material. So if you don't have an AC capable TIG machine, the aluminum bronze, you may not get the results that I do in this video. So just be aware of that. Again, please watch the link in the description to learn how to set up your machine if you have an AC TIG to run aluminum bronze. Now with that said, product-wise, I'll leave the part number down in the description. For these products, I'm not affiliated with them or any other manufacturer. You can feel free to buy any product that you want. I'm not a shill for this company. However, I will say these are both Blue Demon products. The stickers that they included with this stuff, that must be something new. Their marketing person's pretty funny. I appreciate a sense of humor. Anyways, with that said, I'm going to set up and I'm going to do a simple fillet weld, and then we're going to cut it and look at it, and I'm going to show you how you basically don't have any penetration, nor should you with this stuff. So this is what a proper braze should look like, at least the one on the right. The one on the left where it has what would, I guess, be a lack of fusion where it bridged over the root of the joint, that can be pretty typical with bronze brazing, simply because if your heat input and travel speed aren't exactly right, or you're trying to put down too much material, more or less the heat doesn't get far enough in the joint to melt that material down in there. And also, like I stated earlier, this does not work on capillary action where you're going to see braze material between that top and bottom plate. what you do is you keep the heat on the braze material, and then you keep feeding it with more wire, and you move along just like you're welding, and it will follow the heat to a certain extent, but you're not relying on heating an area ahead of where you're brazing and then feeding the filler on that hot material. You're basically keeping the heat on the braze, the bronze, and then you're just using it pretty much like welding. All right, I think you understand what we're looking at here. Let's move on. So as you guys saw, the braze more or less just sits on the plate, and you're not going to get penetration, and penetration is not desirable. You really don't want the base material to mix with the braze alloy, because realistically it's probably going to create voids, defects, or strength related issues. So ideally you should have zero penetration, and it should sit more like a glue or a bead of caulk and not like a weld. Now that you understand a little bit more about that, I'm going to talk really quickly about actual practical uses for this stuff. One of the great things with bronzes and brazing is that since you're not melting your base material, you can join materials that you would never ever be able to weld together under conventional circumstances. Say like titanium to steel. You could actually do that with bronze brazing versus if you attempt to weld it, it doesn't work. The titanium is more or less going to crumble. So it opens up a whole host of things that you can do regarding mismatching materials. You can also braze cast iron, and it's incredibly strong in many cases, which is a great tool to have, because you guys got to remember with cast iron, some forms of it simply aren't weldable. Even with high nickel rods and preheat, they just don't take to welding because of that high carbon content. And since you're not melting the base material with brazing, you can often join two pieces of castings together and not risk cracking, because again, you're not mixing all of those alloys together that don't want to be mixed. Another potential use for this stuff is on a heat-sensitive alloy, so like chromoly. Certain forms of chromoly do not like to be heated very hot, and they don't like to be welded where it brings up the temperature to molten, like super hot, and in cold really fast. Those types of alloys, and it's not just forms of chromoly, but tool steels and all sorts of stuff, that you can use this stuff, and because again you're not melting the base material, and you can control heat input, aka you're putting less heat into it typically than welding, can give you the ability to join those materials stronger than a weld would be, because a weld, that you have a heat affected zone that's far bigger, you have base metal dilution, you have all those things, and brazing can solve that issue of heat sensitivity and heat affected zone problems, all of that grain structure in certain materials. And don't quote me on it, but I believe certain Formula One cars actually used TIG weld brazed or even torch weld brazed chromoly parts on the suspension. And that is likely because the heat affected zone is so much smaller that you don't have that brittleness. Because anyone who's welded on chromoly and a lot of tool steels and a lot of specialty alloys knows that if you don't heat treat the part when you're done, that the weld will never fail, but the part will crack right near the weld under stress. So that's why it pays to have some of this stuff around, because it can help you out in a pinch solving problems. Now, there are some downsides to this type of a product. Now, one of them is the vibration resistance and how good it is under extreme heat. AKA, if you were to weld a cracked exhaust manifold, would this stuff last? Well, its temperature that it flows at is far less than a weld, obviously. Weld requires molten metal. This does not require the base metal to melt. Therefore, this will not hold up likely as good under higher temperature. I would suspect that on something like an exhaust manifold that gets ridiculously hot, aka close to the cylinder head, you may have issues where the welds crack, deform, or fail due to the high heat and temperature cycling, where this stuff will fail, but maybe a nickel rod or some other process wouldn't fail on you. It's something to think of. Another thing is that, well, this stuff is tested, and I'll put up a spec sheet now comparing it to, like, I don't know, ER70 MIG wire. But you got to remember that the results of this is so heavily dependent on your skill and how good of a braze you put down, what base material you're using, and so many other factors that I wouldn't trust this for high liability work without adequate testing. So no, you shouldn't be going and repairing stuff on your leaf springs with this. Just because it will hold together doesn't mean you should do it. So I guess you get the idea on that. Now with all that said, I'm going to start brazing these plates up with this material, and I'm going to do a set of each one with a single pass and a set with a multiple pass, because typically this stuff is far stronger with multi-pass simply because of how it functions. It's not like a fusion process, so oversizing the braze should give us the strength that we're looking for on something this thick. Well, I got all these guys brazed up, and these two were done by my apprentice Owen, and I thought, well, why not take me out of the picture and let him fool around with this stuff a little bit and give this a shot as well. So we're going to be bend testing his as well. So anyways, these over here were silicon bronze. These were the aluminum bronze. Aluminum bronze tends to be more golden color, and silicon tends to be more copper colored. Now this, I probably should have done a little bit better of a job cleaning. There's quite a lot of crap that was floating out of this. And you guys got to remember on AC, which is what I welded this aluminum bronze with, that AC has electrons jumping from the area around where you're brazing to the tungsten, and it has a cleaning action even on normal steel. Now the weird thing is, if you were to try an AC TIG weld steel, you would probably just contaminate your tungsten pretty quickly, but it does work with aluminum bronze. However, if your stuff isn't perfectly clean, you're going to get a lot of crap floating around in the puddle. Single pass went a little bit better, but for the strength, of these, I don't think that's really going to matter, that's a little bit dirty. Now what will matter is this guy right here, which is a multiple pass silicon bronze. I swear that I saw a crack on this and I brushed it and it seemed to have went away. Maybe it wasn't a crack. Just looking at this, it kind of seems suspect, and that brings up a great point, and that is this stuff can be very temperature sensitive. I ran a pass, gave it a couple of minutes, ran a pass, probably didn't give it enough, and ran a third pass. And you got to be careful with not overheating your base material as well as the bronze itself. This stuff you can't really move fast. You kind of want to go low and slow per se, like you want to keep the heat on it and travel at a reasonable pace. This I probably sped up a little bit, and the faster it cools, the higher likelihood I think you're going to get of cracking. And I don't really know for sure if that is a crack. I mean, I can't see it, but I guess we'll find out. The other interesting thing too is the silicon bronze seems to pull a lot more. Like this aluminum bronze pulled a little bit being a multiple pass weld, but not nearly as much as this silicon bronze. So it seems to shrink a lot more in what I'm seeing with the silicon bronze. Well, with that said, what we're going to do is we're going to bend these away from the face just like I would a normal weld in the shop press, and see if somehow this braze can hold on to this 3/8 plate. I mean, the amount of force that this is going to see is pretty much astronomical, so I'd be surprised if a single pass would hold up. However, multiple passes, it's possible it would. All right, let's break these. Up first is a silicon bronze. And not too surprising, looks like the Braze failed. Up next is a multi-pass, and considering how brittle that normal silicon bronze was, I don't have too high of expectations that this is somehow going to hold on. Yeah, I'm going to take a guess and say that that was probably cracked and fairly brittle. So multiple pass with that, fast and hot, probably pretty limited. That's kind of a bummer, but I have a feeling if I did this again, maybe if I used a little bit less heat, it might perform a little bit better. But all right, well, let's go to aluminum bronze. All right, we got the aluminum bronze here, single pass. I'm going to reset this a little bit back further in it. And not too surprising, that also broke. Let's go and try the next one. And that almost held on. It did seem to mostly actually pull out of the base material, but almost. All right, here's Owen's multiple pass braze. This was done with a different aluminum bronze, different companies. I bought that stuff like years ago, didn't have enough to do all the testing in this video. So it'll be interesting to see if this is any different. And it fully bent. Imagine that. All right, let's go to the welding table and talk about what we got. Well, we have some catastrophic failures, and that's to be expected. When you're dealing with stuff like this, it's not like normal metal or a weld where you put the pressure on it and it climbs, it climbs, it climbs, it climbs, and then you'll see like a reduction in pressure or strength, like it's starting to give a little bit and then it fails. This stuff pretty much will hit a pressure and you don't see that and it immediately fails. And again, to be expected. Now, the first one we're going to look at is this guy. Let's zoom in. As expected, the braze did not melt any of this original plate edge, and it did not pull any of the material out of this plate whatsoever. This is 100% just a failure of the braze material. And in this case, I would say this is as good as it's going to get. It's a single pass. Everything looks good. It's consistent for the depth of, well, we can't call it fusion, but the braze got all the way to the root. Everything looks good. And no, this single pass is nowhere near as strong as a typical weld. A typical weld, you'd be able to bend this plate fully and it would not fail. That would be with ER70 MIG, with TIG 7018, no issue. So a single pass of silicon bronze is not nearly as strong as a weld. Now this multiple pass braze failed even easier than this guy, and I think that comes down to there must have been some shrinkage cracks on this or something, and you really got to watch this stuff. I probably should have slowed down, used a little bit less amperage, and maybe it would have worked, but considering how much this pulled that plate, I just think putting that much braze down on something like this is going to be an issue. Now, once again, the root pass of this is good. There is no melting of the base material whatsoever, and the braze itself failed. However, again, I think it was pre-cracked. It looks like it may have pulled a little bit of material off the base plate. Hard to tell. Realistically, this I don't believe would have taken much of a bend at all, to be honest, over what this did. This stuff is just not nearly as strong as aluminum bronze. Speaking of aluminum bronze, so this is something you definitely would never want to see a weld do. It peeled it up like a bead of caulk, and if you look at that, I've never seen a weld do that, but that's pretty cool. That's definitely gonna, maybe I'll cut this off and make a keychain out of this or something. So anyways, this single pass actually did bend this 3/8 plate quite a bit before it catastrophically failed. It did not take anything out of the base material whatsoever, and it did make it to the root of the joint. Aluminum bronze, without question, is definitely stronger than silicon bronze. So if you need a brazing alloy that is super strong, consider using this over the silicon bronze. Now the multiple pass braze, this one is quite interesting. So maybe I didn't clean this base material good enough, but it seems to have bit into the plate and tore part of the plate out with it, which is pretty unusual. It did not do that on the base plate whatsoever. And this almost made it to a full bend. I mean, you can see how much bent that is before it failed. I think maybe if I just had a little bit better base prep, maybe a little bit better heat control on this, that this would have survived a full bend, which is pretty amazing when you think of it, because there's a lot of welding rods out there, 6010, 6013, 6011, 7014. Even your typical self-shielded flux core wire will fail far before this did. So this is actually incredibly strong. Now, this guy right here, which was again done with aluminum bronze, a different brand, and likely had maybe a little bit better surface prep, hard to say, was able to survive a full bend just like a 7018 stick weld on this without failure. Now, you still see the start of a crack up here, which is typical of welds as well. All of that stress of this plate curling kind of gets focused here and it starts tearing through the base material. However, it did pass a bend. Now this is gigantic compared to like a single pass 7018 or ER70 MIG wire weld that would have passed this. So this is a lot of material holding this together. But hey, the stuff in multiple pass is actually pretty strong. And I would say borderline will perform similar in this test as a normal weld. So that's pretty wild. All right, let's go over to the vise and we're gonna break this guy in a different way. I'm gonna break this guy that Owen welded to the face so that we can look at the internal structure and also to kind of give a relatable exercise to prove how strong this stuff really is. You got to remember there is no fusion in there, therefore it's very easy for this plate to kind of use that braze as a lever and break it. And I'm going to give it a whole bunch of whacks with this hammer and we'll see. I'll definitely break it, but it should be fairly strong. And that it is. So this isn't nearly as strong as a weld when bent towards the face. Now, had I put a oversized braze on it, it would be a little bit harder to bend. But that lack of penetration in there just makes it far easier for this to lift up and use this braze as like a fulcrum point. So if you do braze something, you got to keep that in mind. If you don't have access to both sides of it, you will see a reduction in the strength, aka the breaking strength towards the face of the braze. All right, let me finish breaking this. So looking at this, everything looks perfectly fine. The braze went directly to that edge. That edge is completely clean and untouched. We didn't have any base metal dilution, and the braze itself failed. Again, not nearly as strong as a weld, but for a lot of circumstances, this might actually work pretty good for you, and it's stronger than I would have thought being bent this way. And you got to remember, this is only a single pass and a pretty small one at that, because it was done with 1/16, not 332 like this rod. So pretty strong, all things considered. All right, let's go to conclusion. So in conclusion, what did we learn today? Well, hopefully you learned that brazing can be incredibly strong and that certain types of brazing are stronger than others. Now keep in mind, this aluminum bronze wire that I used for that is one particular type. There are multiple types of aluminum bronze, so it pays to look into what they're good at. And that might explain why the one that I did failed at a fairly high load and this one did not. It's possible that it was a different type of aluminum bronze. Like there's A1, A2, A3, I believe. So it's hard to know, and this stuff is never stamped or labeled with what it is, which is why it's very important to keep this stuff in the original tube it came in so you know exactly what it is. And when this was brazed, it was just basically loose filler. I knew that it was aluminum bronze. However, what type? Anybody's guess. Based on what I saw in the testing here, I got a couple recommendations for you guys. The first one being, silicon bronze is a fine product, but watch your heat input, watch your travel speed, and if you see evidence of cracking, you're best off cutting it out and then redoing it, or you can wind up with a situation like I have, like I did earlier, where more or less it failed a lot quicker than it should. And that's something that's kind of unique somewhat to these products. Like when you use, say, 7018 or ER70 wire, your weld isn't going to crack on mild steel, maybe if you quenched it with water. This stuff, you have to pay attention to the details or you can have cracks or other undesirable side effects that severely weaken what you put down. So in that respect, it takes more skill, more attention to detail, etc., than welding, in my opinion. And that's one of the reasons why you're not going to see this stuff used too much on critical type work, simply because the end result is highly unreliable, in my opinion. Now, we saw that aluminum bronze is incredibly strong, stronger than I would have thought. I mean, it survived the full bend on 3/8 plate with not really that big of a braze, but then this one failed, and It's just, there's a lot of variables at play here, and welding, like with 7018 or say TIG, is kind of, I don't want to say foolproof, but the results are very reliable and predictable. And there's just so many variables with this. I would not recommend using this on critical stuff. However, if you have cast iron or something you want to make out of multiple types of metal and you're worried that the welds are going to crack, this stuff can be a lifesaver. Like, you could even make artwork with titanium and stainless and steel with this product, and or both of these actually, and join them from an artistic standpoint in a way that wouldn't normally be possible. So there are a ton of uses for this stuff. Speaking of which, if you use this stuff fairly often and you have a particular use that you want to share with people, feel free to leave it in the comments. I'm sure people will get all sorts of ideas from other people that use this stuff, so it'd be great. You'd be helping out them as well. Oh, and I almost forgot. Another great use for this stuff is on emergency repair on copper, like eye terminals for electronics or motors or something. A buddy of mine came to me once and had a custom part made for some controller. I don't know what it was, but it had a couple terminals that were copper, where copper wire went in it like an eyelet. And he could not find ones that would fit his situation, and he broke a couple of them because, well, he was an idiot and was a little aggressive taking stuff apart. And I was able to braze back together the copper, and he was able to get the unit, whatever it was, running long enough to where when the replacement parts came in, that he was able to swap it. So using it on copper can be very beneficial to fixing things as well. So with that said, hopefully you enjoyed the video. If you got any comments, questions, thoughts, feel free to leave them in the comments. Otherwise, until next time.